So, whenever we were talking in Calculus 1 about single integrals, you probably talked about Riemann sums, where Riemann sums is where you just add up the areas of rectangles. And the areas of those rectangles approximated the area under a particular curve. And so if we took the limit as the number of rectangles increased to infinity in the Riemann sum, and the size of the width of the base of the rectangle approached 0, then in this limit, adding up the areas of the rectangles gave you the area under a curve. So, this is my little Desmos demonstration. That we've got this red curve, and in green are the rectangles you would make for a left-sided Riemann sum. And you notice that adding together the areas on of the rectangles doesn't exactly give you the area under the curve, because there's like some area in between the top of the rectangles and the curve. And then like in this case of the rightmost rectangle, there's a little bit of extra rectangle that's not under the curve. And so adding up the green rectangles gives you an area of 8.37, but the actual area under the curve is 8.59. So we've got like a 2.5% error. But as I allow the number of rectangles to increase, and I choose like, let's say 16 rectangles, then my approximation gets better. Right now I only have a 1.23% error. It's over 1%. And if I do 32 rectangles, right, then my error goes down to 0.6%. And so the more rectangles we have, the closer that approximation gets. And in the limit, this would be exactly the area under the curve. So what I want to show you is that if we talk about double integrals, we can do double Riemann sums. And with the double Riemann sum, we're going to eventually approximate the volume under a surface. So rather doing the area under a curve, we're going to be calculating the volume under a particular surface over a region in my domain. So let me show you this little tool from GeoGebra. And let me set this to like smaller numbers. Okay, so what we're looking at here is we've got this red surface. Let me see if I can rotate it. Yeah, okay. We've got this red surface that lives mostly above the XY plane, right? And if I wanted to approximate the volume that was bounded in between the XY plane and the red surface, it's kind of a really strange shape of a solid. But what I could do is I could create a bunch of little square prisms, right? Like I have here. And I set the height of the square prism to be the value of this function, or the height of the curve, somewhere inside the square, right? And so I think here it's doing like midpoint approximations. So it's taking the midpoint of each square, and then it goes up so that the height of the square prism is at the surface itself. And adding up the volumes of these rectangular prisms, adding up the volumes of these square prisms, it's not going to be exactly the volume under the curve, because there's some errors. There's some places where the curve is taller than the square prism, and there's some other places where the square prisms are taller than the surface. But it's pretty close. It's a pretty decent estimate of what that volume should be. If I actually really want to find the volume of this, I would take the limit as the number of those square prisms go to infinity, and the width of the square prism in both the x direction and the y direction goes to 0. And whenever I do that, these square prisms are going to be more and more and more closely hugging the surface. And so adding up the volumes of all of the square prisms is going to be closer and closer to the volume bounded between the surface and the xy plane over that domain. Does that make sense? So if I ever say the words double Riemann sum, I mean a Riemann sum where I'm adding up all of these little square prisms. Okay, so that's sort of the geometric intuition behind what we're doing and why we're doing double integrals. So, for a single integral over some function, this is like the limit as n approaches infinity and delta x approaches 0 of a certain sum where k is allowed to go from 1 to n of f evaluated at some point within each of those intervals times the width of the interval. So that's what was like the single variable function case where we were doing areas under curves and relating the integral to a Riemann sum. In the case where we're doing double integrals of a function, this is like taking the limit as the number of square prisms goes to infinity and the width and length of the squares that make up the base of the square prisms go to 0. And then the way I would write this Riemann sum is it's the sum as k goes from 1 to n of the sum where, let's say, j goes from 1 to m of my function evaluated at some x value that lives inside a given interval and a y value that lives inside a given interval times delta x delta y. So that's what I mean by a double Riemann sum. You don't have to memorize all these symbols. I'm not going to include that on any kind of exam. But remember that we're talking about adding up those little square prisms, all the little volumes. Okay, so Gabriel, you're a little bit behind because you just walked in. You can watch this recording later if you want to catch up. But this is the idea of what we're doing whenever we do a double integral.
Oh, yeah.
It's kind of like a Riemann sum, but instead of adding up the areas of the rectangles, we're adding up the volumes of all of these rectangular prisms to get the volume under a surface. We're not talking about areas under curves anymore.
Yeah.
We're talking about the volumes under a surface. And by the way, I didn't mention this yet, but notice where the surface dips below the xy plane.
Mm-hmm.
These prisms go down. Just like that would count as like negative area in the Riemann sum for a single variable function, those count as like negative volume when we talk about a function of two variables. Okay? And so that would actually be subtracted from my Riemann sum. It would be subtracted from my double integral in the same way you learned in Calculus 1.
So just like in normal Calculus 1 integrals, you would also have a margin of error?
Yeah. So there would be places where these prisms are sticking up above the surface and places where the surface is actually taller than the top of the prism. And so there is going to be error in this kind of Riemann sum approximation. But the double integral itself has no error because we're taking the limit as the number of these little prisms goes to infinity. Okay. It's not enough to say that the area of the base goes to 0, because the area of the base could go to 0 if only the delta x goes to 0, right? But we have to say the limit as delta x and delta y go to 0 if you actually want to have the definition of the double integral, so that's important. But anyways, these symbols is what you would write if you were trying to describe in symbols what's happening with adding up those little prisms.
So xk is the point between xi and xi plus 1, and then yj is the point between
Yeah. So in this picture, it's using the very center of the square as the height of the square prism, but the limit definition works even if you take any point inside the square, right? Which is any point inside the x interval along with any point inside the y interval. Okay. So, if you see this, that's saying take the double integral over the region R of the function 1 minus x squared minus y squared. And the little dA is saying take a little differential chunk of area in my domain there. So this is a function of two variables. It's a function of x and y. And so the domain of this function is the xy plane. And so whenever I say I'm integrating over the region R, this region R is part of my domain. Okay? So what we talked about on Thursday is I could take just the area of that region R by doing something like the integral from 0 to 1 of the integral from 0 to 1 of 1 dx dy. That would give me the area of this square, but hopefully it's obvious to you that the area of the square is 1 anyways. And so if I want now not just the area, but the volume that's given by this paraboloid, or the volume that's bound between the xy plane and this paraboloid as it sits over this region in my domain. This is the double integral that I'm going to try to evaluate. So it's up to you then to decide, given this dA, do I want this to be dx dy, or do I want this to be dy dx? Okay? You have to choose that. In a lot of these problems, it doesn't matter. In a lot of these problems, you could solve it either way. In this problem, it really, really doesn't matter because the integrand is symmetric with respect to x and y, and so it will not change even the solution at all. And then it's also up to you to figure out, okay, for this region R in the plane, what do the bounds of integration have to be? And in this case, I chose 0 and 1 because in the x direction, the minimum for x is 0 and the maximum for x is 1. And then in the y direction, the minimum for y is 0 and the maximum for y is 1. Okay. So let's look at and see what this paraboloid looks like, 1 minus x squared minus y squared. If I can pull up the GeoGebra calculator. So z equals 1 minus x squared minus y squared. So that's my little paraboloid. And I want to calculate the volume bound between this paraboloid and the plane over a certain region where I say, x is allowed to be between 0 and 1, and y is allowed to be between 0 and 1. And I can already tell that part of this paraboloid is going to be above the xy plane and part of it's going to be below the xy plane, right? Like, there's going to be like a little sliver here that actually dips below the plane. Because if I plug in x equals 1 and y equals 1, this is 1 minus 1 minus 1, which is a negative value for my f function. Negative value for that z coordinate on the surface. And my actual question is not asking me to find the volume. It's asking me to evaluate this double integral. And so it's fine if I'm adding up part that's positive and part that's negative. Again, I'm not worried about the volume. I'm just worried about actually calculating the integral. So this is not exactly a volume question. It's just saying, let's take this and evaluate it. So it should be pretty easy, I think. If I take the antiderivative of this with respect to x only, then that's going to be x minus 1/3 x cubed minus y squared x, evaluated at 1 and 0 dy. Because remember, when I take the antiderivative with respect to x, I just pretend that y is a constant. So if I plug in x equals 0, all of those terms go to 0. I only really care about plugging in x equals 1. And plugging in x equals 1 is really easy. This would be 1 minus 1/3 minus y squared dy. And then I take the antiderivative with respect to y, and it would be y times, 2/3 minus 1/3 y cubed, evaluated at 1 and 0. Again, if I evaluate it at 0, then it's just 0, so I only care about evaluating this at 1, and that's really easy. So if I take the volume of the paraboloid that's above the plane and subtract the volume of the paraboloid that's below the plane, or at least I'm talking about the volumes that are bounded between the surface and the plane, then it ended up being 1/3. Any questions about that example? Okay.
If you were to calculate the volume in this case, how would you do it?
Ooh, that's a good question. So first, I would say, let me set this surface, right? Z equals 1 minus x squared minus y squared. If I wanted to calculate the total volume bounded between the surface and the xy plane, then I would say what x and y values give me a z value of 0. In other words, where does this surface intersect my xy plane? And solving for that means x squared plus y squared equals 1. So that would mean that the square root of x squared plus y squared equals 1. So that surface is going to intersect my xy plane at the unit circle, right? That's the intersection between my domain, the xy plane, and the paraboloid. So this region in the first quadrant, bounded by my unit circle, this is going to have positive volume when I take that integral. And then this region out here, in the rest of this square, this is going to give me negative volume when I take the double integral. So I need to split this up. Instead of just having one double integral, I'm going to have two double integrals, and that way I can be sure to flip the sign on that part. Right? So for my one double integral, let's do the positive part first. I would say, let me let x go from 0 to 1. And then if I allow x to be between 0 and 1, then y can be anywhere between 0 and the square root of 1 minus x squared. X squared plus y squared equals 1. I subtract the x squared and then take the square root. Yeah, okay. So that would be my upper bound of integration. And again, what I'm integrating is 1 minus x squared minus y squared. First with respect to y and then with respect to x. So that would be the positive part. That would be the part that's above the xy plane and inside this unit circle. To get the negative part, I would say, okay, minus the double integral from, okay, let's allow x to go from 0 to 1 again, and then I'm going to make y be between the square root of 1 minus x squared and 1. And then I would integrate 1 minus x squared minus y squared. And again, I put this negative sign in front because I'm trying to add the volume, but it's a negative volume, so I have to subtract the negative volume to end up adding that to my total volume.